Hello and welcome again to Chem in 3. Today we look at the trends in first ionization energy as you go across period 2 of the periodic table. The general trend as you go from lithium to neon is one of an increase in the energy required to remove 1 mole of electrons from 1 mole of gaseous ions to give you 1 mole of positively charged ions and 1 mole of electrons. That is the first ionization energy. And the general trend is one of increase because as you go across, the effective nuclear charge increases from lithium to neon. In neon, for instance, the total nuclear charge is 10. And the shielding electrons, meaning that to remove that first electron, you must overcome the significant attraction caused by the 10 protons. Whereas in the case of lithium, the effective nuclear charge is only 3 protons minus the 2 shielding electrons, which is just 1, which means that lithium has a much smaller first ionization energy than neon. And this is what accounts for the general trend. But what about these 2 spots here, number 1 and number 2? These 2 disruptions here in the overall trend of increase. First, let's look at beryllium. And beryllium has this electron configuration with 2 electrons in its 1s2 orbital, 2 electrons in its 2s2 orbital, and nothing in the 2p energy level, which is a sublevel of the second energy level. But when you move from beryllium to boron, then that extra electron for boron goes into a slightly higher energy level. And because it's at a slightly higher energy level, it becomes that much easier to remove this electron. So the first ionization energy of boron is just that little bit lower than the first ionization energy of beryllium, which has nothing in its 2p orbital. The second point to note is as we go from nitrogen to oxygen. Here you have the electron configuration of nitrogen, showing 1s2, 2s2, and a 2p sublevel nicely filled with 1 electron in the x, 1 in the y, and 1 in the z. But when you move from nitrogen to oxygen, that extra electron that you would have in oxygen, which again is going to be the first one to be removed in ionization, that extra electron has to fill into one of these 2p levels, disrupting this nice stable trend of 1 in each sublevel. And this electron is that much easier to remove than the first electron from nitrogen, because in nitrogen you have 1 electron in each of the x, y, and z, whereas in oxygen you have that extra electron added to one of these, disrupting the stability, if you will, and making it that much easier to remove that first electron in oxygen. So these are the reasons behind these 2 disruptions in the overall trend of increase. Now the periodic table is filled with examples of periodic patterns. So I would like you to consider a similar graph for period 3 of the periodic table. Then as you get that graph, I would like you to compare it to this one, and then to suggest reasons for any discrepancies that you find. In addition to that, I would want you to do some research and go beyond the first ionization energy. Look at successive ionization energies for certain atoms. I'm going to give you some atoms to consider. When I say successive ionization energies, I mean, if this is the first, then the second ionization energy would be removing an electron here from this singly charged species. And the third ionization energy would be removing an electron from x2 positive, and so on. And the trend goes on. So now I would like you to research the first 5 ionization energies of sodium. I would like you to research the first 5 ionization energies of aluminum, and I would like you to research the first 12 ionization energies of chlorine. When you get this data, put the data for each one on a graph, graphing first, second, third, fourth, fifth ionization energy on one axis and the amount of energy on the other axis. And then observe the trends for any discrepancies or unusual patterns. Then I would like you to suggest possible explanations for what you observed, bearing in mind that this is going to provide evidence for the Bohr model of the atom, which says that electrons occupy distinct energy levels like 1, 2, 3, and so on.